Consider the following statement P and Q. Statement P is if matrix M is equal to this, then M is singular. Statement Q is let S be a diagonalizable matrix if T is matrix such that S plus 5T equal to ID. Here I is identity and D may be a real number, then T is diagonalizable. Which of the above statements hold true? We have to find true statements P or Q or both are true or false. Option or statement P is very simple. If M is equal to this, then we need to tell about singularity of this matrix. Singularity of this matrix can be easily by either rank or determinant, because this is 3 by 3 and it's considered as a lower size matrix, so finding determinant is easy than compared to rank. If it will be higher size, then we should approach by a rank. So I'm going to use determinant. So determinant along first row 1, 9 2 is 18, minus 3 4 is 12, minus 1 9 minus 4, and plus 1 3 minus 2. It will give you 6 minus 9 minus 4 5, so minus 5 here, and 3 minus 2 plus 1. So 2 not equal to 0. So M is singular? No, M is non-singular. M is non-singular. So statement P is false here. Now come to the statement Q. Let S be a diagonal matrix if T is a matrix such that S plus 5T equal to ID, then T is diagonalizable. We need to tell about diagonalizability of S plus 5T equal to ID. Here D is a constant. S plus 5 times T equal to ID. Because this is identity matrix, or identity matrix may be considered as a scalar matrix if we multiply diagonal element by any scalar number or non-zero number, then it will be a scalar number. So either it is identity or it is scalar matrix, so you can write any one. So it is not about it is not the concern, it is identity scalar, because this term will not affect this question. As S is diagonalizable, so recall some properties of diagonalizability. If a matrix is diagonalizable, then its algebraic multiplicity of all eigenvalues must be equal to geometric multiplicity of all eigenvalues, and hence sum of algebraic multiplicity is equal to sum of geometric multiplicity. Second one is, if it is a diagonalizable, then S can be represent PDP inverse, where P is a non-singular matrix. It is not from statement P, it is a different notation for matrix. P is any non-singular matrix, any singular matrix, or there will be exist a non-singular matrix space such that S can be written as a PDP inverse, and D is a diagonal matrix. So if S can be written as a PDP inverse, then we can write S plus 5 times T equal to, I am using identity because it is convenient to solve this problem. 5 times T is equal to identity minus S, and S can be written as PDP inverse, or you can write identity here. So took Now come to the concern 5t is equal to identity matrix minus p d p inverse. D is diagonalizable or diagonal matrix, and this is also diagonal matrix. So it can be written as I minus D, or identity you can write P outside and P inverse. This will be also a diagonal matrix, because difference of two diagonal matrix is again diagonal matrix. You can write D prime in place of I minus D. So 5 times T equal to P D prime P inverse, where D prime is a diagonal matrix of correct size. If we divide by 5, then this can be written as T equal to 1 upon 5 P D prime P inverse. So singularity, non-singularity remains same. So P is non-singular matrix. So T is also diagonalizable matrix. So this statement is true here. P is false and Q is true only. So option C is our right choice.